So your question was, is there any other methods? Yes, we have a graphical method, but now we are learning the concept. How could we construct the shear force diagram and the bending moment diagram using this method, which is the equation method? So we establish or develop those equations, and then we know the range within which we have to know it. It's not like an optional thing, and we follow the easiest way to construct. Anyway, at the end of the day, when you become an expert in as an engineer, you become an expert. You don't need to prove to me that you can establish those equations. But the importance of being able to establish these equations is to sometimes you might not be able to graphically guess the actual what do you call the shape of the shear force or the bending moment, and probably sometimes it's not about that. Sometimes you need to just for certain location you need to identify or know the exact value of the moment. So all the time you need you have to have an equation to evaluate the to get the actual value for the moment and the shear force. Graphically, you won't be able to evaluate the actual force if of course, when I'm talking about examples where the loading is complex, loading condition is complex, you have to make use of the equations. So you have to come up with equations to evaluate shear force and and bending moment. Okay, uh, but if you're asking me like if I could solve it with the same method in an easier way, if that was your question, I don't know. That was your question with the same method, but easier way, easier. Is there anything easier? That what you meant?
No, totally not when Bakari.
No, a graphical method. Now we are learning this method. So if I specify an example and I ask you to construct a shear force diagram, bending moment diagram using equations, you have to establish, I need to see the equations. It's not just about drawing the graph like shear force diagram and bending moment. I need to see the equations. I need to see the signs and your assumptions and see if you are capable of establishing correct equations for evaluation, for shear force diagram evaluation and for bending moment diagram evaluation. So that's the thing that now we are learning. Okay. Any other questions? Any other questions? Now we have established the shear force diagram. Again, I remind you of the beam. Beam is a simply because I will establish another the other equation for the moment diagram. Okay, so we had a shear simply supported beam loaded with a point load at midspan. Okay, at midspan, and then hold on, and this is a hinge supported at both ends here and there. Okay, hinge or roller. Okay, and then we have these two supports, and the load was a point load P, and then we got the reaction upward. Okay, use engineering mechanics. Um, okay, I mean equilibrium equations to solve this. If the problem is complicated, then you need to solve it that way. And then you have P over 2. P over 2 would be your reaction at both sides. So we have constructed that the shear force diagram would look like something like this. I constructed again, just to remind you, this is the shear force diagram. Okay, I have a P over 2 from here up to midspan, then P over 2 in the negative side up to the end. Okay, up to the end. Okay, so I make sure that my result is okay. I see that the P over 2 is the reaction, go upward, so it would go and close the shape. And this P is going downward, so from this point to this point downward, and is closing the shape, okay? And I have like this reaction is going upward, so it close, okay? So go. This is shear force diagram. I know the value of each zone, and we have positive and negative. The positive and negative is based on our textbook assumption. A positive, so when you see a shear force diagram, okay, most of the textbooks adopted this convention. So we know that if you take a section here, the shear force is downward. Why? Because we have assumed that the downward is positive. Okay, if you take this zone from here to here, the shear force is negative. Okay, why? If you take a section, and then the shear force is upward. Okay, and the section, make sure that this section we're talking about this section, when the section is taking the left side of the beam. The section is taking the left side. Okay. Okay. So that's how we know. Then now we need to establish the moment equation. Okay. Again, for the moment, we also need to the same thing you have applied for the shear force, you apply for the moment. Okay. The same thing we have applied for the shear force, you apply for the moment. So for taking the moment, again, we need to establish zone 1 and 2. Same, zone 1, zone 2. Same thing, zone 1 and zone 2 would be the same for the shear force and bending moment. We labeled this at SFD, as I told you, shear force diagram, okay? And you have to specify the unit if it was a numerical example. So it's, is it Newton or kilonewton? So you have to specify it. If Newton, Newton. If kilonewton, kilonewton. Now I established something else, which is the moment diagram. Before I establish the moment diagram, okay, let me just clear up to have some space for the equations. What I need, just partition the page into two sides so that I establish my equations on one side and draw on the other side. So let's say from range 1, which is, we know x in between L over 2 up to 0. Okay, 0. Sorry, L over 2 was not included. Okay, L over 2 was not included. So I need to erase it. Okay, oh. Okay, L over 2 is not included. So now I need to establish the equation. So what I do, I draw a section, okay, a section, and then, okay, this is my support. I have a reaction upward, which is P over 2, okay? And the zone is prior to the load, so the load is not included. And this is where I take the moment about. The section is this, okay? So there would be an X, okay? I need to consider this X, okay? And then what I have is I have a shear force that doesn't play any role, so I don't need to congest my drawing with shear force and anything else, just get the moment. I assume my positive is moment is like acting clockwise. So this is my moment, clockwise. I assume it that way. I don't know if it is wrong or not, but I assume it to be this way. Did I miss anything? No. Okay, if I didn't miss anything, so I consider this to be Z1, Z1, or Z1, okay? Zone 1. So summation of moment, I consider the counterclockwise to be the positive, okay? Counterclockwise to be the positive. Summation of moment at the section is equated to 0, okay? Summation of moment at the section, at the section, you write it as SEC, okay, dot, is equal to 0. I assume the counterclockwise to be positive. So what I have here, a force, definitely, a force about this cross section would develop a moment. So I have P over 2 is a force to convert it into moment times X, okay, because the distance is X. And then what sign convention? I assume the counterclockwise. Is this a counterclockwise moment? No, so it's negative. Okay, what else? Do I have anything else up to here? It seems I don't have. So that's all what I have, right? Yeah. So, and then the moment is clockwise. Based on this assumption, it would be negative M. Negative M. And I equate it to 0. Do I have anything that I missed? Any force, axial, doesn't play an important role. V goes off because the moment is about this section. What else? Do I have anything? No. So that's it. So now I just then rearrange it. So I get M on one side. I shifted M to this side. So it becomes negative, becomes positive, and then is equal to negative P over 2. Is equal to negative P over 2 times X. So that means I have a negative sign, which makes my assumption for this moment to be wrong. So what I do, I say M is equal to P over 2 times X, okay, times X positive, and it's not clockwise, it's counterclockwise. It's counterclockwise. So this M wrong, my assumption was wrong. So the M is counterclockwise. Okay. Okay, when X is equal to 0, if I plug in 0, M would be equal, so at X 0, when X is equal to 0, if I plug in 0 instead of X, then I'm gonna get P over 2 times 0. So that would make my moment equal to 0. Okay. Okay. The other thing, what else I have? I have when X is equal to L over 2. Is it included? Yes, included. L over 2? No, it's not included. So it's not included. So I just get X when X is equal to, you could say, close to L over 2. Close to L over 2 is like L over 1.9, right? Well, L over 2, 1.9. So I get the value for this moment at close to where the force is located. It's prior to the force location. Okay, so I have now established something. So I need to draw the bending moment just before this is the beginning, this is the end. What I got is like, how to say, what I got just now is like, I know that the moment is 0 at the beginning, okay? And if I plug in this value, L over 1.9 into X, how much I'm gonna get? It's close to P L over 3.9, okay? 3.8 maybe, okay? Right? So it's close to that, 3.8. Okay, so I know the value. Is it positive? How do I know if it is positive or not? As I told you, the moment is counterclockwise. Okay, I have this moment is counterclockwise. Okay, this moment is counterclockwise. As I told you, would it make a smiley face? If it makes a smiley face on this beam, if I draw an imaginary moment opposite to it, would it make a smiley face? Yes, it makes a smiley face. So it's positive. So now I know up to prior to this point, up to here, I could say, I know the value is positive. Okay, I know that the value is positive. And then I look at the equation. The equation is like M is equal to P over 2 times X, right? P over 2 times X. So is it a curve or an inclined line, or how it looks like? Is it how it looks like? For sure, if you link these two, right, you know that how it looks like. So it's like a line, right, with an inclination up to here. Okay. So now again, what I need to establish for zone 2, the moment for zone 2. The moment for zone 2. The moment for zone 2. Okay. Now I need to establish the moment. Sorry, I just removed it mistakenly. I need to establish the moment for zone 2. So what I do for zone 2, I also need to establish, I will remove this equation, okay? For the zone 1, I remove it. okay, because we know that we have established it. I don't have enough space to establish the other equation. I remove this zone, okay. So I just add zone 2. I need to add something to zone 2. I just make use of the same drawing, okay. I consider that this x has gone beyond L over 2, so the point load, I could see it over here. I have a point load, right? So it has gone beyond. So I have a force, and then I need to establish, this is the force, P, right? So what I have over here, shear doesn't play any important role. The section moment, I assume it to be clockwise, the positive, okay, M is positive. I consider it to be clockwise. I now establish the for zone 2. Zone 2 is in between. Let me change the color to black. So zone 2 would be x in between, now included. L over 2 is included, up to L. Up to L is included, both sides. So I have, okay, so to take the moment, summation, again, summation of moment, counterclockwise. Counterclockwise is the positive, summation of moment about the section equated to 0, and then I establish my equation. My equation, I have P over 2 to make it the moment, has to be multiplied by a distance, which is x, and what kind of force it would give a clockwise, so it's negative based on my assumption, assumption over here, so it's negative, and then I will have a force which is P, right? So the P would be positive or negative. It would be positive based on my assumption. The P has to be multiplied by a distance. I need to pay attention at the distance for P because X is starting from here, right? So if this is like, for example, if this is like if X is equal to L over 2, then I should have P is equal to 0 because P is exactly at midspan. So what I do, I say that my P is time L all the time. I subtracted from L over 2 because this distance L over 2 is all the time, sorry, not L, X, what I meant is X. This is an X, so why? Because it's all the time, X is the range is L over 2 negative, okay, minus subtracted from L over 2, so that when you consider X over L, when X is equal to L over 2, the P has no role. This force has no role at this section. That's the only way. When P exceeds L over 2, when that means when, sorry, X exceeds L over 2, so X is greater than L over 2, yeah, that's correct. So that would be the distance, the acting distance for this force, okay? The X is always greater than, not always greater, is equal at one point, and then afterwards is always greater than L over 2. So when it becomes greater, when it is equal to L over 2, it has no effect on the section. When it is greater than L over 2, then we have to subtract it from L over 2, so that we subtract it from this much of X, from this, sorry, not X, this constant distance between the support and the point load itself, which is L over 2, so that when X is more than L over 2, this distance will be calculated within the equation, okay? This distance will be calculated within the equation, okay? So is that correct? Yes. Sign convention, we assume counterclockwise. Does it make a counterclockwise moment? Yes, so positive, okay. I established this, I established that. I have assumed the moment to be clockwise, so I would say negative M. So that would make it negative M, minus or subtracted from M. So minus, write it down next to it, negative M, and then the whole equation goes to 0 or equal to 0. Okay, now I just rearrange and get M on one side. So once I rearrange, I'm gonna get P, if I get M to the other side, it would become positive, and then I would end up with negative P over 2, okay? times x plus p times x negative minus L over 2. If nothing wrong, I can now make sure. If I have x is equal, the range is L. If I have L, so this would go into PL over 2, and if this is L, this would be PL over 2, but negative. Negative will eat the positive, so M would be equal to 0. So on this side, change the color. On this side, I have proved to myself my equation is right. On this, when the X is reaching its final, it's the other side of the beam. That means the end side of the beam or the right side of the beam. When X is equal to L, I'm gonna get M is 0. Okay, I'm gonna get M is 0. When the M is equal to L over 2, when because it's included here, so I just replaced just plug in L over 2 instead of X. So I think L over 2 with L over 2, so this would go to 0, and this would be equal to L over, right? If L over 2, right? So this would be equal to L over 2 times P over 2 negative. There's something wrong with the equation then. Just check what's going on. Okay, so as soon as this example is over, then the lecture would be over. Okay. Okay, so let me check if there is anything that is wrong with my assumption. There must be something wrong with my assumption. Negative when L is equal to L over 2. This is correct. And this is negative when L is equal to L over 2. L over 2. When L we have proved when L is L negative, when L is negative, yeah, 0. So when L over 2, when it's L over 2, why is it negative? Is it negative? If I move it to the other side, the M would be, so there's something wrong with the assumption. Counterclockwise, M, I assume it to be clockwise, the positive, so I gave it negative sign, so I shifted to the other side, it would become positive. So this is negative, and this would remain positive. Nothing wrong with it, right? I'm supposed to get, in fact, when I plug in L over 2, I'm supposed to get this L over 4. So if I plug in L over 2, I'm gonna get L over 4, but in negative. Sorry, why is it in negative? Why is it in negative? Negative? Aha, okay. If it is in negative, think it's negative, positive, negative. So it's causing a smiley face. Aha. My assumption is wrong. So that means, okay, I get that M is equal to negative when L is equal to L. So that means my assumption is not, if I plug in L over 2, this term would go and this term would be negative. So my m, I have to change the direction of m into the counterclockwise. So it becomes counterclockwise, okay? Counterclockwise, okay? And the value is equal to PL over 4, okay? PL over 4. So counterclockwise would give me a smiley face, right? Counterclockwise would give me a smiley face, so that would make it positive, right? So positive, so that's how my diagram would look like, okay? So you complete it, and it becomes like this. So you're gonna end up with a triangle, okay? Okay, any question? Do we have anyone who's about to leave? Yahya, if you want to leave, you can leave if you have no question. Yahya, if you want to leave, you can leave if you have no question.
Okay, sir. Thanks.
Okay, you can leave. Anyone who has no question can leave. Anyone who has questions or a question can stay.
Thanks, teacher.
Vale. Vale. Yes. No question? And then just stop.